Okay, so the next speaker is James, also known as Ben Worrell, who also did a postdoc at Tulane, but came out of Oxford and then came back and has been here ever since as well.
So yeah, so I've changed the title of my talk subtly from the program. So if you know, well, if you've seen the program, so in the program the title is Ultimate Positivity is Decidable for Linear Recurrent Sequences. But kind of crucially I should say simple, because otherwise it just wouldn't be true. Or rather I wouldn't know it was true. So I mean, I guess Gordon has the ultimate get out clause here because the title of his talk, if you look in the program, the title of this talk may change. So there's some circularity there. So all right, yeah. So these three people. This was so Joel had Prakash back in the day. I had Prakash yesterday. So we went to dinner at Green Templeton College and. Actually, so a mystery occurred at that dinner that's actually been revealed to me this morning. The answer to the mystery is, so Prakash said that the waiter is not filling my glass with wine. I keep on giving him looks, like pointed looks, and he's not filling my glass with wine. So can you do something? So eventually I said, well, do you mind filling my guest's glass with wine? And so you had some wine, and then that was the white wine, and the red wine came, and again he wasn't filling the glass with red wine. So I had to ask again for the red wine. Anyway, so this morning I got an email from the domestic bursar saying, I'm sorry for the embarrassment to your guest, but you have to sign in for wine. You have to when you sign in for dinner, you have to request that your guests have wine. So in fact, so it's all my fault. But anyway, so enough with the technical stuff. So that concludes my talk. That concludes the slide part of my talk. So I'm going to do again a Joel style on the board. So let me hold this up. So I don't know if you know this book. This is a book, Automata Theoretic Aspects of Formal Power Series by Arto Salomar and his, I think, then student Matti Soitola. So Salomar and this kind of Finnish school, so and Soitola and also Rosenberg were interested in formal power series. So formal power series, let's say, with weights in the integers is a function from sigma star to the integer, sigma of finite alphabet. And so one of the results they proved in the book is a kind of Kleene type theorem where they show that for formal power series, the set of rational series is equal to the set of recognizable series. So rational, so there are regular expressions and there's an analog of, so you can see these as generalizations of languages, and there's analogs of regular expressions, and you can define rational sequences. So the rational sequences are got by taking polynomials, so such power series with finite support, and closing them under some Cauchy product and Kleene star. So Kleene star would be some n equals 0 to infinity fn. And recognizable is just accepted by automata. So in this case they'd be weighted automata. Okay. And they proved this Kleene theorem, and they were further considered the special case where you have the alphabet of size 1. So in case you have an alphabet of size 1, what does a formal power series look like? Well, sigma star is just then the natural numbers, so it's just a sequence of integers. So in this case, what do the rational equals recognizable sequences look like? So, well, we can easily say what recognizable looks like in this case. So, I guess it's approaching the limit. So, thinking of this sequence here, what does it mean it's recognizable? Well, it's acceptable by an automaton, and a weighted automaton. When you flush out the definition, what it means is the following. So there is a square matrix M, a row vector alpha transpose, think of these as the initial states, and a column vector eta of final states, and the nth entry of the sequence is equal to that. So this looks like something that Joel had drawn on the board in his previous slide. And of course, you will then know this, well, you may then recognize that in this case, in fact, the set of sequences that are recognizable in this sense are precisely the set of sequences satisfying a linear recurrence. So, so F is an LRS, a linear recurrent sequence, if and only if it's recognizable in this sense. So let me just for terminological sake, just be explicit about this. So a linear recurrent sequence, so the n plus k term is going to be a combination of the previous k terms. So like Fibonacci, etc. So a linear recurrent sequence. So these are precisely these rational recognizable sequences. So, okay, so these occur in the book, and in the book, so one of the central 4 open problems that the book lays out, is they lay them out one after the other, is 4 decision problems. And here we're interested in decidability and complexity of these problems. And these are as follows. So so it's given a linear recurrent sequence Fn. So as input to a decision problem, let's say I'm working over the integers, I just get the recurrence of the initial values that determine the sequence, and the 4 problems that they ask are the following problem. So does there exist an n such that Fn equals 0? Do there exist infinitely many n's such that Fn equals 0? Is it the case that for all n, Fn is greater or equal to 0? And for, does there exist an n for all n greater or equal to n, Fn is non-negative? Okay, so 4 decision problems on linear recurrent sequences concerning the behavior of these sequences. Let me say, these have names, 3 of them have names, so let me say, part of the motivation for some of these problems is that a linear recurrent sequence, linear recurrent sequences are very natural generalizations of polynomials. So a linear recurrent sequence has a closed form expression as an exponential polynomial. So a linear recurrent sequence can be written as in the following form. So here, any recurrent sequence can be written in the following form, where these are polynomials, and these are the roots of the characteristic equation of the characteristic polynomial of the recurrence. So you can think of this, you could call this an exponential polynomial, because there are polynomial terms here, and there are exponential terms. And so, these are so natural problems you're interested in polynomials. Does a polynomial have a root? So this problem is kind of an analog of the problem, does a polynomial have a root? And then this is about the asymptotic growth of these expressions. Okay, so let me just observe. So Prakash asked a question. So Joel was talking about single matrix, and then Prakash asked, well, what if you have 2 matrices? Well, they observe, in the book here, one thing they observe is that these problems all make sense for general rational power series over sigma star, and they're undecidable in case the alphabet has size 2, so then they're interested in alphabet size 1, where these questions are all open. Okay, so this problem here is called Skolan's problem. So this is probably the most famous of these decision problems. So even though, I'm kind of focusing on this book, this has been studied also in the mathematical community independently. This problem here is called the positivity problem. So is the LRS positive? and this is ultimate positivity. So are all but finitely many terms positive? And this is what I want to talk about in this talk. Okay, so let me just say something about the terminology here. So why is this called Skolan's problem here? Well, there's a beautiful theorem by Skolan, Mallet, and Leck, which characterizes the set of zeros of a linear recurrence sequence. So Skolan, Mallet, Leck say the following. So let Fn be a linear recurrent sequence, and let me look at the set of indices where the sequence is 0. Then it describes the structure of this set as semi-linear. So it's a finite set union finitely many arithmetic progressions. So here f is finite, and these things here are arithmetic progressions. Okay, so the proof of the theorem will tell you this for any LRS, but the proof is not constructive. So if you give me an LRS, the proof won't tell you all details about these sets. So it's partially constructive. So in fact, what the proof will tell you is that given an LRS is whether these arithmetic progressions here are present. It will tell you their period. So this enables you to solve this decision problem. So this decision problem here is decidable. So given an LRS, are there infinitely many zeros? So this was shown by Burstell and Mignot. So Mignot was a number theorist. They showed this was decidable, and they did that by extracting the kind of constructive element here, showing that, okay, given an LRS, I can see whether these arithmetic progressions are present. If they're present, there are infinitely many zeros. If they're not, then there are only finitely many zeros. However, if they're not present, then you're left in a situation where you've got a linear recurrent sequence with a finite set of zeros, and you don't know whether that finite set, well, you need to decide whether that finite set is empty or not if you want to decide Skolan's problem. Does this have a zero? So this is open, so it's known to be decidable for linear recurrences of low order. So the order of the recurrence here, so the recurrence that I deleted had order 4, so Fibonacci sequence has order 2. For recurrences of order 4, this is known to be decidable. For 5, it's open. Now, so positivity has kind of, well, it has some of the flavor. So one observation here is that this problem, decidability of this problem implies decidability of this problem. So trivially, so if Fn is a linear recurrent sequence, and I'm interested in whether it equals 0, well then I can observe that Fn squared minus 1 is also a linear recurrent sequence. And this is equal to 0 if and only if this at some n is not greater or equal to 0. So, I mean, that's a linear recurrent sequence, so it can be shown that this is a linear recurrent sequence. And so if I could decide this, then I could decide this. So, in fact, so Joel and I, in this year in Soda, we showed decidability of this up to order 5, positivity, for linear recurrences of order 5. So now this is order 4, decidable up to order 4. So and now I'm waiting for, usually at some point someone's going to, hopefully someone will say, well, but if people are following,
But you squared it.
yeah, I squared it. Oh, okay. Yeah, I squared it, so I increased the order. So
People are one step ahead.
yeah. Actually, I just realised I've actually lost track of time. When did I start?
You're about halfway through.
I'm halfway through. Okay. Okay. Now. Okay. Good. Yeah. So now, so this is characteristic of the field. You have these results for low order. Well, here we have unconditional. This is decidable at all orders. And so what I want, the main result I want to talk to you about now is this is a result that's just been accepted to ICAP, is that this is decidable now at all orders again for simple linear recurrence sequences, so for simple LRS. Okay, so I'll just say something about this hypothesis in a second. But I mean, what you can take away from that is that somehow you've got decidability here, and here you've only got decidability at low order. And I think the kind of intuition is that so this is positivity for all but finitely many terms. So this is, it's saying that ultimate properties are somehow easier to decide, so properties in the limit. So I mean, let me just say for a second that you might say, well, I mean, given that you can decide this, why can't you, given that you can decide ultimate positivity, why can't you decide positivity? Because you've got an LRS and you feed it to your ultimate positivity algorithm and it says, well, if it's not ultimately positive, then it certainly isn't positive, okay? If it is ultimately positive, then you just take the n beyond which it's guaranteed to be positive and you check all the values up to that n mechanically. But the key point is that our algorithm that solves this is non-constructive. It doesn't tell you this n, this threshold. So the algorithm will tell you this sequence is ultimately positive, but it won't tell you the point from which it becomes positive. And that's because the algorithm itself is predicated on non-constructive results. So everything here seems to come down to Diophantine approximation, and a lot of results there are non-constructive. So, okay, so now, yeah, what shall I say? I shall say something about the complexity of this problem. So, so the complexity, so we showed this, well, I should say something about simple. So, simple LRS, well, one way of saying it is that the roots of the characteristic polynomial are simple roots. I mean, a more kind of maybe informative way of putting it is, well, the LRS is given by an exponential polynomial expression, so if it's a simple LRS, then these polynomials here are just constants. So I could just write, let's say, AI. So this really simplifies the analysis, so you've just got a sum of exponential terms. Yeah, okay, so let me say something about the complexity. So of this problem here, so it's decidable for simple LRS. The complexity is, okay, so it's for all R hard and in P space. So it's in polynomial space. Now, for all R, so what this is for all R is the notation I'm using for the decision problem for the first order theory of the reals. So the universal sentences over the first order theory of the reals. Of the real closed fields. So I'm interested in fields here. So even though this is a kind of Diophantine problem, it's about, I mean, I'm talking about integer linear recurrent sequences. The lower bound, so the decision problem, so given a sentence over the reals, a universal sentence, you decide whether it's true or not. That's the problem is at least as hard as this, and the complexity upper bound is in P space. So I mean, what does that mean? So this problem is known to be within P space. So can he show decidability of this in P space? So this is somewhere between co-NP and P space. And in fact, I mean, well, I mean, we still haven't given up hope of proving that the problem is actually complete for this. As a decision problem, it's equivalent to this. Okay, so an important element of the decidability proof uses decidability results over the real field, and also definability results about the structure of functions that you can define in this logical theory. So let me wrap up by saying so we have this nice result for ultimate positivity, which is nice in that it shows this, decidability at all orders without restriction on orders. Now we have here show the decidability at order 5 for positivity. Now, the question is, well, we have also we have decidability of positivity here, and we also have decidability of ultimate positivity at order 5 in this solar paper. Now, here, the reason we can only go up to order 5 with ultimate positivity is we don't make the assumption of simplicity. So the question is, well, I mean, this is a crucial assumption, and what goes, so you might say, well, what goes wrong at order 6? So if I have a non-simple LRS at order 6, so non-simple LRS at order 6, why can't you prove decidability? So it's a very constrained problem, just to look at the linear recurrent sequences of some fixed order, but now without the hypothesis of simplicity. And essentially the reason, so one has a kind of hardness result that says, if you had an algorithm to do this, then you would know things that, I mean, it's known that people, I mean, it's just known that people don't know, so the mathematicians don't know. So let me just state that slightly more formally than I've just done. So, so it's to do with the Diophantine approximation. So let me take a real number. So Dirichlet's theorem says the following. So take any real number you like, and Dirichlet's theorem says, well, how closely can you approximate it with rationals? Well, you can approximate it as closely as you like with rationals, I mean, dense. But suppose you want, well, and clearly I can get within 1 over n of x, but Dirichlet says, well, you can get within 1 over n squared for infinitely many m and n. So that was Dirichlet. And in fact, this theorem was improved by shortly afterwards by Hurwitz, who said, in fact, for any x, you can get within 1 over root 5n squared for infinitely many n. Is this spelling? Yeah, okay. It's obvious, sorry. Okay, so now, essentially, but beyond that, so for specific real numbers, so for certain real numbers, well, for almost all real numbers, there are infinitely many solutions to this inequality for arbitrary large C. But for real numbers, one doesn't know, so this, I mean, for a given real number, one can define what's known as the LeBrons Constant. So let me just have this as my final definition. So the LeBrons Constant is the following. So it's the infimum of C such that the inequality has infinitely many solutions. In n and n.
You want to put the C on the numerator?
Yeah. Well, I could make it super. Yeah. Okay, so the Lagrange constant of a real number x is the infimum of those constants C such that this inequality here has infinitely many solutions in n and m. So for instance, for all real numbers x, I know that with 1 over root 5, I have infinitely many solutions. If I make this constant smaller, the inequality becomes more challenging, maybe I only have finitely many solutions. So it's a measure of how well this number can be approximated with rationals. And essentially, not much is known about the Lagrange constant of specific numbers. So, so for pi, I mean, it's known to be between 0 and a third, but nothing more is known. And essentially, if you had an algorithm that would solve this ultimate positivity problem, then you could compute Lagrange constants for a whole wide family of transcendental numbers. I mean, and it's clear that people don't know how to do this. So essentially, the value of this result was linking this decision problem here, this Diophantine problem, with this, and telling you to stop studying it. But as Joel said, there are many kind of, So I mean, I don't want to say that it's a subject that people shouldn't study. I mean, there are many interesting open problems here to do with kind of restricted aspects. Okay, so I'm going to stop there.
Question?
So, one of the scariest parts of mathematics is the theory of parallel line approximation. I bought a book and put it on my shelf now, looking at it from afar, I've not approached it closer than that. I'm wondering, in your applications, can you treat this theory as a black box, or do you actually need to delve into some of those techniques?
You can treat it. You have to delve in a little bit. So it's specifically. So there are applications of the of subspace theorem where you have to do some manipulation or some inductive proofs, but the results themselves, we're using the results as given.
Another question?
Just for a laugh, I was going to ask you if you were sure that Q was a field.
I'm sure that Q is a field, however, and I also know that Z is a group as well. So unlike